A rock sat in the ground for 4 billion years. It was dull, reddish-brown, heavy, and completely unremarkable. Farmers stepped over it. Children kicked it aside. Builders used it to fill gaps in walls. Nobody looked at it twice because it looked like nothing. Like dirt pressed hard. Like the earth itself. And buried inside that rock was the material that would one day hold up the tallest buildings ever constructed, carry freight trains across continents, form the hull of ships that cross oceans, and eventually get hammered into the very machines that pull us out of poverty. But for most of human history, the rock just sat there. The question is not simply how we eventually found iron. The deeper question, the one that changes how you see every bridge and skyscraper you have ever walked past, is how an ancient person with no chemistry, no periodic table, no university, and no tradition to follow could look at a dull red stone and somehow, through fire and accident and 10,000 failed attempts, pull a metal out of it that Stone Age technology had no business producing. The answer is one of the strangest stories in human history, and it starts not underground, but in the sky. To understand how radical the discovery of iron was, you need to understand the world before it. For nearly 2 million years, human technology was defined by stone. Flint, obsidian, quartzite, these were the materials of survival. They could be chipped into edges sharp enough to cut meat and skin animals, but they were brittle. A stone axe could split wood, but one hard blow against bone and it shattered. Stone tools could not be reshaped once made. If the edge broke, the tool was finished. Then, roughly 5,000 years ago, something shifted. People in the Middle East and Eastern Mediterranean discovered how to smelt copper. This was itself a small miracle, realizing that certain greenish or blue-tinged rocks, when placed in a very hot fire, would surrender a soft, shining liquid metal that hardened into a shape you could choose. Copper could be hammered into thin sheets. It could be cast in clay molds. It could be sharpened and resharpened, but pure copper is soft. A copper blade bends rather than cuts when it meets something tough. And then metallurgists, though they would not have called themselves that, made a second discovery. If you mix copper with tin in roughly a 9-to-1 ratio, you get something harder and tougher than either metal alone. You get bronze. Bronze was the dominant material of civilization for nearly 2,000 years. Bronze swords, bronze shields, bronze plows, bronze chisels. The Bronze Age is the age of the first cities, the first writing, the first empires, and all of it ran on a metal alloy that needed 2 ingredients. And that was the problem. Copper was reasonably abundant, but tin is not. Tin deposits are scattered in a handful of specific places on Earth, parts of what is now England, Central Europe, and Central Asia. For civilizations in Egypt, Mesopotamia, and the Aegean, obtaining tin required organizing long-distance trade networks across thousands of miles of land and sea. Ships carried tin ingots from Cornwall in Britain down through the Mediterranean. Overland caravans hauled tin from mines in Afghanistan toward the ancient cities of the Near East. These supply chains were fragile. A single war, a collapsed trade agreement, or a storm that sank a merchant fleet could leave an entire civilization without the raw material to make its most important tool. Egypt depended on trade. The Hittite Empire depended on trade. The Mycenaean palaces depended on trade. An element that would solve this problem was sitting in the soil beneath every single one of their feet. They just had no way of knowing it. Iron is the 4th most abundant element in Earth's crust. It makes up more than 5% of everything beneath the ground we walk on. Mountains contain it. River sediments carry it. The reddish color of clay soil in many parts of the world comes from iron oxide, rust essentially mixed into the earth. There is virtually no place on the surface of Earth where iron ore does not exist within a reasonable distance, and yet for thousands of years of human civilization, people who had mastered bronze, built pyramids, written literature, and developed sophisticated legal codes could not do a single useful thing with iron. The reason is deceptively simple. Iron on Earth almost never appears as a metal. Unlike gold, which occurs in nature as shining nuggets in riverbeds, or copper, which sometimes appears as raw reddish metallic chunks in rock, iron is almost never found in its metallic form on the surface of the planet. The reason is chemistry. Iron has an extremely strong attraction to oxygen. Given any exposure to air and water over geological timescales, iron metal converts to iron oxide, what we recognize as rust. Every trace of naturally occurring metallic iron that ever existed on Earth's surface has long since been chemically transformed into dull reddish stone. What ancient people saw when they looked at iron ore was not a hidden metal. They saw red rock, brown rock, heavy rock, rock that looked exactly like rock, because as far as their experience could tell them, it was rock. There was one exception, and it came from space. Nickel-iron meteorites are fragments of the metallic cores of asteroids, bodies that broke apart during the early solar system. When these fragments survive the fall through Earth's atmosphere and land on the surface, they bring with them something that does not naturally exist on Earth: native metallic iron already in pure usable form, alloyed with a small percentage of nickel. These space rocks are extraordinary objects to encounter. They are far denser than ordinary stone. They are magnetic. When struck with a rock hammer, they do not chip or shatter, they dent. They have a metallic gleam when cut or polished. Everything about them is wrong for a rock. Ancient people who found meteorites recognized immediately that they were dealing with something unlike anything else on Earth. And they were right. In ancient Egypt, iron was given a specific hieroglyphic name that translates directly to metal from heaven, or stone of heaven. This was not poetic language. Egyptian scribes were describing the only iron they had ever encountered, which genuinely had come from the sky. Ancient Sumerian texts used a term for iron that combined the signs for sky and external, metal from outside from beyond. Hittite ritual documents described iron as the black iron of the sky. Across cultures separated by thousands of miles, the same understanding emerged independently. This material was celestial, and because it came from beyond the sky, it was treated accordingly. The earliest iron objects in the archaeological record predate what we call the Iron Age by more than 1,500 years. These objects were not made from ore pulled from the ground. They were hammered from meteorite fragments. In predynastic Egypt, from cemetery burials dating to around 3,200 years before the Common Era, archaeologists recovered 9 small tube-shaped beads. When scientists analyzed these beads using modern chemical testing, they found very high concentrations of nickel, a chemical signature that is unmistakable evidence of meteoritic origin. These beads were hammered from a piece of iron that had fallen from space. In the tomb of the Egyptian pharaoh Tutankhamun, buried around 1,300 years before the Common Era, archaeologists found a dagger with an iron blade. For decades, debate surrounded this object. X-ray fluorescence analysis eventually provided the answer. The blade contained nearly 11% nickel and trace amounts of cobalt, a composition that matches closely with a known meteorite recovered near the Egyptian coast. The king of Egypt was buried with a blade made from a rock that had fallen from the sky. During the Bronze Age, this kind of iron was rarer than gold. Ancient Assyrian trade records from Anatolia show that iron commanded prices up to 40 times that of silver by weight. Iron rings and objects appear in palace inventories alongside jewelry. They were diplomatic gifts between kings. They were symbols of extraordinary status in an age when bronze was already the metal of power. This changes the way you have to think about iron's discovery. Before any human being figured out how to extract iron from the ground, iron was already known. It was touched, shaped, and treasured, but it was sky metal. Ore iron, the iron that would eventually remake the world, required something entirely different to unlock. It required a kind of fire that did not yet exist. Here is the thermodynamic fact that delayed the Iron Age by thousands of years. Copper melts at 1,085 degrees Celsius. Bronze melts at approximately 950 degrees Celsius, lower, because alloying metals with tin reduces the melting point. The kilns and furnaces of the Bronze Age were built to hit these temperatures. Pottery kilns, designed to fire ceramic at high temperatures, routinely reached between 1,000 and 1,150 degrees Celsius. This was enough to liquefy copper and bronze, allowing them to be cast in molds, which is how bronze objects were made. Pure iron melts at 1,538 degrees Celsius. That gap, roughly 400 degrees between what Bronze Age furnaces could achieve and the temperature required to melt iron, is not a small engineering challenge. It is a completely different class of problem. The furnaces that could smelt copper and cast bronze, no matter how perfectly operated, were physically incapable of liquefying iron ore. When early metalworkers, and there is archaeological evidence they tried, placed iron-rich rocks into copper-smelting furnaces and waited for liquid metal to collect at the bottom, nothing happened. The iron did not melt. It did not flow. It just sat there, red-hot, stubbornly solid, offering nothing. Every logical inference from the knowledge available at the time said that iron was a useless rock. The idea that this rock could be turned into metal required something that no one had yet discovered, a completely different kind of extraction that did not need melting at all. The path toward iron was not a single discovery. It was a gradual accumulation of furnace knowledge that took place across generations, in cultures that did not know they were moving toward anything in particular. The first major improvement was charcoal. At some point, metalworkers stopped burning raw wood and began burning charcoal instead. Charcoal, wood that has been slowly heated in the near absence of oxygen to drive off water and volatile gases, is almost pure carbon. It burns hotter and more consistently than raw timber, it produces less smoke. Inside a furnace, it raises the thermal ceiling significantly. The second improvement was enclosure. Early fires were open hearths, but stone and clay-walled structures tall enough to create a chimney effect changed everything. A column of rising hot gas inside an enclosed shaft pulls fresh air in from the bottom. The taller the shaft, the stronger the draft. The stronger the draft, the more oxygen reaches the burning charcoal. More oxygen means higher temperatures. These furnaces were not designed with this logic in mind. The logic came after, from archaeology and experimentation. At the time, builders who made furnaces taller simply noticed that the fire burned better. The third, and perhaps most critical improvement, was the bellows. Leather bellows pumped air directly into the base of a furnace through clay nozzles. This forced airflow could raise furnace temperatures dramatically compared to natural draft alone. Sustained bellows operation could push temperatures inside a shaft furnace to 1200 degrees Celsius or higher. None of these improvements were made with iron in mind. Bronze smelters wanted hotter furnaces to smelt copper more efficiently, fire clay pottery more evenly, and melt metals with less wasted fuel. They were solving immediate practical problems. The cumulative result across centuries of refinement was a furnace capable of something its builders had not intended. What happened next was probably not observed by a single person on a single day. The likeliest reconstruction, based on archaeological evidence and experimental metallurgy, is this: a copper smelter operating a charcoal-fueled shaft furnace with bellows added iron-bearing rocks to the furnace. This may have been intentional. Iron-rich rocks were sometimes used as a flux, a material that helps separate impurities from copper ore during smelting. Or the furnace walls themselves may have been lined with iron-rich clay and stone. In either case, the iron ore entered a furnace burning at temperatures somewhere between 1000 and 1200 degrees Celsius. At those temperatures, iron ore does not melt. But something else happens. Burning charcoal in a partially enclosed environment does not combust completely. With limited oxygen, the carbon in the charcoal produces carbon monoxide gas rather than carbon dioxide. And carbon monoxide is chemically aggressive toward oxygen-bearing compounds. As it rises through the furnace shaft, carbon monoxide encounters iron oxide, the ore, and strips the oxygen atoms away from the iron atoms. It does not melt the ore. It chemically reduces it, transforming it in the solid state from an oxide compound into metallic iron. The chemical reaction requires no melting. It requires only that carbon monoxide and iron oxide be in contact at sufficiently high temperatures. The product is not a pool of liquid iron at the furnace bottom. What forms instead is a spongy, porous mass of metallic iron particles fused together, still riddled with glassy slag, trapped in the shape of the ore that was reduced. This mass is called a bloom. When someone opened the bottom of that furnace and extracted what was inside, expecting to find copper or slag, nothing useful, they found instead an object that had never been seen before. It was dark and porous. It did not shine. It looked almost nothing like metal. But when struck with a hammer while still hot, it did not chip or shatter. It deformed. It was ductile. It was metal. Something new was in the world. What strikes you when you study how ancient ironworkers operated is how much they learned through observation alone, and how precisely they learned it, despite having no framework that would explain why any of it worked. Smelters learned to identify high-quality iron ores, not from chemical analysis, but from weight, color, and where they were found. Dense, dark rocks found in certain geological formations reliably produced better blooms than lighter, reddish, earthy material. Inside the furnace, they read the flame. Experienced smelters could judge temperature by the color of the fire visible at the top of the shaft. Bright yellow-white indicated optimal reduction conditions. Dull red indicated insufficient heat. They learned the rhythm of the bellows that corresponded to a productive run. They knew from the viscosity of the liquid slag draining through the tap hole at the base whether the furnace chemistry was running correctly. The proportions of charcoal to ore, the height of the charge, the pumping rhythm of the bellows, the timing of when to stop the operation and extract the bloom, all of this was learned empirically, over generations, and transmitted as craft knowledge through apprenticeship. There were no written metallurgical texts, there were no formulas, there was observation, memory, and the oral tradition of the workshop. This is worth dwelling on. The ancient bloomery ironworker did not understand carbon monoxide reduction kinetics, iron oxide phase transitions, or the thermodynamics of solid-state diffusion. But they had mapped the input-output relationships of the process with extraordinary precision. They knew what to put in, what to do with the fire, and what should come out. They just did not know why any of it worked. The technology that became the standard tool of iron production for thousands of years across most of the world was the bloomery furnace. A bloomery was a vertical shaft, usually somewhere between 1 and 2 meters tall, built from fired clay, fieldstone, and straw binders. It had an opening at the top through which charcoal and crushed ore were charged in alternating layers. Near the base, one or more clay nozzles connected to leather bellows allowed forced air to enter the burning fuel bed. At the very bottom, A taphole allowed liquid slag to drain out, or the lower wall could be broken open after each run to extract the bloom. Inside, as crushed ore descended through the descending charcoal bed, it passed through progressively hotter zones and encountered ascending carbon monoxide gas. The ore was chemically reduced step by step, from hematite down through intermediate iron oxides, ultimately to metallic iron. Without ever becoming liquid, the metallic iron particles formed near the hottest zone of the furnace, where the bellows air entered. These particles sintered together under their own weight and the furnace heat, forming a consolidated spongy mass. The silica impurities in the ore reacted with a portion of the iron oxide to form a liquid iron silicate slag, which drained away from the bloom. A single bloomery run might take several hours. The bloom extracted at the end weighed anywhere from a few kilograms to tens of kilograms, depending on furnace size and ore quality. And when it came out, the work was only beginning. A raw iron bloom is not usable iron. It is metallic iron shot through with liquid solid slag, porous as a sponge, soft and structurally incoherent. Left as is, it would crack and crumble. The transformation from bloom to useful metal was the blacksmith's work. And it was hard work. While the bloom was still at near white heat, somewhere above 1,000 degrees Celsius, it was transferred to a stone anvil and beaten with heavy hammers. The blows had a purpose. They squeezed slag out of the porous interior, driving it out through the surface as the metal compressed. They collapsed the internal voids, bringing metallic iron particles into direct contact. At those temperatures, the touching iron particles fused together at the atomic level, a process called solid-state diffusion welding, without any melting involved. Repeated hammer blows broke up the coarse crystal structure of the iron, refining it into a stronger, more organized grain pattern. The product of this sustained, physically demanding process was wrought iron, a low-carbon metal with excellent tensile strength and exceptional toughness. It could be bent severely without fracturing. It absorbed shock loads. It could be shaped and reshaped repeatedly by heating and hammering. And it could be worked to an edge that, while not as hard as the best bronze, did not require tin from the other side of the world. But the full potential of iron was still hidden. The next discovery, the one that made iron definitively superior to bronze, came not from a deliberate experiment, but from yet another accident embedded in the normal practice of the forge. The fact that ancient people, without a single piece of modern scientific knowledge, could puzzle this out through sheer observation and persistence is, in itself, one of the most remarkable things about our species. If you're finding this journey as fascinating as we do, consider subscribing to the channel and hitting the like button. It genuinely helps us keep going deeper into stories like this one. Wrought iron has a problem. It is tough, but it is soft. A wrought iron blade edge subjected to heavy use, cutting through bone, chopping through hardwood, meeting another metal object in combat, will deform and lose its sharpness quickly. Well-hardened bronze, by comparison, holds an edge better. The element that bridges this gap is carbon, and ancient blacksmiths had no idea it existed. What they did know, through accumulated experience, was that iron left in contact with burning charcoal for extended periods of time behaved differently than iron that had not been exposed this way. It grew harder. It became stiffer. A blade that sat in a hot charcoal hearth for hours, being heated and reheated, came out with different properties than one processed quickly. The reason, which no one understood for thousands of years, is this. When iron is heated above a certain temperature, around 900 degrees Celsius, it undergoes a change in its internal crystal structure. In this state, called austenite, the iron lattice has gaps between its atoms that are exactly the right size to accommodate carbon atoms. As the hot iron sits surrounded by burning charcoal, carbon atoms migrate from the charcoal surface into the metal, filling those gaps. The iron absorbs carbon. A small amount of carbon, less than 1% by weight, changes the mechanical properties of iron dramatically. With enough carbon, iron becomes steel. Steel can be hardened by heating it to the right temperature and cooling it rapidly. Plunged into cold water, the carbon-enriched iron locks into a crystal structure called martensite, which is extraordinarily hard enough to cut and scratch bronze without difficulty. The ancient blacksmiths who first produced this harder metal had not planned to. They noticed it. They found that blades made from certain sections of a bloom, or treated in specific ways in the forge, were harder than others. They developed practices, longer heating times, specific quenching routines, particular fuel-to-metal contact techniques that reliably produced the harder material. They called it by different names in different languages. They knew how to make it. They simply did not know, and had no framework for understanding, that the reason it worked was a chemical element called carbon diffusing into the atomic lattice of the iron. For several centuries after ironworking was developed in Anatolia and the Levant, roughly between 1500 and 1200 years before the Common Era, it remained a secondary technology. Bronze still dominated. The infrastructure, the skill base, the trade networks, and the cultural prestige all belonged to bronze. Iron tools and weapons were produced and used, but they did not yet define the age. Then, around 1200 years before the Common Era, something catastrophic happened. In the space of roughly 50 years, nearly every major civilization of the Eastern Mediterranean collapsed or was severely disrupted. The Mycenaean palace system of Greece disintegrated. The Hittite Empire, one of the dominant powers of the ancient Near East, ceased to exist. Coastal cities from the Levant to Cyprus were burned. Egyptian records describe invasions from groups described as the Sea Peoples. The interconnected palace economy of the Late Bronze Age, which had sustained those long tin trade routes, fell apart. The exact causes of this Late Bronze Age collapse remain debated by historians. Climate stress, internal social pressures, military migrations, earthquakes, and the cascade effects of disrupted trade networks are all implicated. What is not debated is the result. The tin supply collapsed. Bronze production across the region crashed. The material that had powered civilization for 2,000 years became difficult and expensive to obtain. Metalworkers facing a shortage of bronze looked at what was available locally. Iron ore was everywhere. Bloomery furnaces, already known, could produce usable metal from local rocks without any imports. The transition to iron, which might have taken several more centuries under stable conditions, was accelerated by necessity. A civilization that had a choice between bronze and iron largely chose bronze. Civilizations facing a tin crisis chose survival. What emerged from the crisis was a technological landscape dominated by iron. And over the next few centuries, as blacksmiths in the Mediterranean and Near East refined their techniques, iron proved to be not just an adequate substitute, but definitively superior to what it replaced. The comparison between iron and bronze is not one-dimensional, and the historical records show that the transition took time precisely because unrefined iron was genuinely not as good as well-made bronze raw. Uncarburized wrought iron is soft. A wrought iron sword, measured on a standard hardness scale, registers significantly lower than a work-hardened bronze blade. Early iron tools bent in use. They were inferior. This is why the Iron Age did not begin the moment bloomery smelting was discovered. The technique for converting iron into something better than bronze took centuries to develop, but carburized, quenched, and tempered steel, the iron-based material that blacksmiths gradually learned to produce, was in a completely different category. A properly heat-treated steel blade achieves a hardness 2 to 3 times greater than the best bronze. It holds an edge longer, resists fracture better, and can be made lighter for the same strength. And then there was the economics. Bronze required copper and tin. Tin demanded trade routes spanning continents. The material was expensive enough that metal armor, weapons, and agricultural tools were largely limited to elite military and wealthy agricultural classes. Mass armies could not be equipped with bronze. Only a fraction of a society's labor force could afford metal tools. Iron ore existed nearly everywhere. Charcoal could be produced from forests in almost any region of the world. A village with a bloomery and a blacksmith could produce its own iron without importing anything. The cost of iron tools dropped as technique improved. A peasant farmer could own an iron plow. A common soldier could carry an iron spear. The metalworking knowledge that had been concentrated in palace workshops began to distribute itself across ordinary communities. This democratization of metal, hard to overstate its significance, changed agriculture, changed warfare, changed the distribution of productive capacity across human societies. When iron became cheap enough for a farmer to own iron-tipped tools, the productivity of land cultivation increased dramatically. When armies could be equipped with iron weapons at mass scale, the nature of military conflict shifted. The village blacksmith that appears in so many cultures across history was not simply a craftsman. In the ancient world, the blacksmith was a figure of near-magical significance. To any observer without chemical knowledge, the blacksmith's work was inexplicable. They took dull, reddish rocks, put them into a fire, worked the fire with bellows, extracted a shapeless, spongy mass, heated it again, hammered it for hours, and produced a blade or a plow tip or an axe head that was harder and sharper than anything that had previously existed. No visible transformation in the rocks prepared you for the metal that came out. The process was hidden inside a fire. Across world cultures independently, ironworking became associated with divine power. In Greek and Roman tradition, Hephaestus and Vulcan, the divine blacksmiths who forged weapons for the gods, were figures of both awe and ambivalence, possessing power so great they had to be lamed or isolated. In West African Yoruba tradition, Ogun is the deity of iron, warfare, and metalworking, revered as the patron of blacksmiths and hunters. Celtic mythology gave the smith god Goibniu the power to forge weapons that never missed their mark. In Norse tradition, the dwarf smiths who forged the weapons of the Aesir were the most technically skilled beings in existence. These are not coincidences. They reflect a consistent response across cultures to the same phenomenon. A person who could transform rock into metal possessed a category of knowledge that was simply beyond normal comprehension. The blacksmith shop was the closest thing to alchemy that the ancient world actually delivered on. Iron technology did not emerge from a single origin and spread outward. Multiple civilizations, largely independently, developed ironworking traditions that produced genuinely distinct innovations. In China, metallurgists took a path that diverged sharply from the Near Eastern bloomery tradition. Chinese furnace technology advanced to the point that, by around the 6th century before the Common Era, furnaces could reach temperatures high enough to fully melt iron, to produce true liquid iron. When iron is fully melted, it absorbs carbon to a much higher level than wrought iron. The result is cast iron, containing between 2 and 4% carbon by weight. Cast iron has a much lower melting point than pure iron, roughly 1150 degrees Celsius, and can be poured into molds to produce complex shapes. It is brittle, but extremely hard and ideal for certain agricultural applications. By 31 years into the Common Era, an official named Du Shi used water wheel power to drive the bellows of blast furnaces, a mechanization of iron production that Western Europe would not achieve for another 12 centuries. In India, metallurgists developed a technique for producing what became known as woot steel. By sealing wrought iron together with organic carbon sources inside clay crucibles and heating them at high temperatures for extended periods, Indian smiths produced high-carbon steel ingots that, when forged carefully, developed distinctive patterns of microscopic carbide bands. The blades made from this material, exported across the Indian Ocean and traded throughout the Middle East and eventually Europe as Damascus steel, were famous for combining extraordinary hardness with flexibility. The technique remained so closely guarded that European metallurgists were unable to reproduce it until the 19th century. In sub-Saharan Africa, particularly in the Great Lakes region and West Africa, independent bloomery traditions developed before the Common Era. African smelters in some regions engineered tall natural draft furnaces that preheated incoming air before it reached the charcoal bed, achieving high efficiencies without mechanical bellows. A thermodynamic design principle that was not formally articulated in European engineering until much later, iron was not one story. It was many stories arriving at related conclusions through different routes. The broad adoption of iron tools across farming cultures fundamentally changed what was possible in agriculture. The heavy moldboard iron plow represented a qualitative leap over wooden plows tipped with bronze or stone. Wooden scratch plows could turn light Mediterranean soils, but the dense clay soils of northern Europe and much of Asia resisted them. An iron moldboard plow could cut deeply into heavy soil, turn it over completely, and bury surface vegetation, dramatically improving fertility and weed control. Regions that had never supported large-scale grain farming became agricultural zones. Human populations that had never had enough food began growing. Iron axes and adzes made forest clearance practical at scales previously impossible. Land that was forested became farmland. Iron sickles cut grain faster and more cleanly than stone or bronze tools. Iron chisels and saws made precision carpentry and stone masonry achievable by ordinary craftsmen, not just those with access to expensive bronze tools. Iron nails made structural carpentry stronger and faster. Iron fittings and chains extended the range and load capacity of wheeled transport. Cast iron cookware, produced in China from quite early in the iron tradition, allowed cooking methods previously impossible with ceramic. Every profession touched by the material found itself able to do more, faster, with less. Not immediately. The transition was slow, but cumulatively. Across centuries, the shift was total. A world built around stone and bronze became a world built around iron. The bloomery furnace, for all its ingenuity, was limited. Each run produced a relatively small bloom. The process was labor-intensive and discontinuous. Scaling up required more furnaces and more workers, not a fundamentally different process. The blast furnace, which emerged in Europe and China through separate developments over the medieval period, changed this. A blast furnace is a continuously operating version of the bloomery concept, but large enough and hot enough to fully melt the iron, producing large volumes of liquid pig iron that could be tapped from the base. Chinese furnaces achieved this by the early Common Era. European blast furnaces became widespread around the 13th and 14th centuries. Pig iron contained too much carbon to be directly used for most purposes. It was hard but brittle. Converting it back into workable low-carbon steel required additional steps, initially using techniques like the puddling process developed by Henry Cort in 1784, which stirred molten pig iron in an oxidizing atmosphere to burn off the excess carbon. Then in 1856, Henry Bessemer patented the converter that carried his name, a vessel into which cold air was blasted through molten pig iron, burning off carbon and silicon through the heat generated by the chemical reactions themselves. In minutes, tons of pig iron became structural steel without any additional fuel. The Bessemer converter made mass-produced structural steel economically viable for the first time. The skyscrapers that defined modern cities, the railways that connected continents, the ships that made global trade a daily reality, all of them became possible because Bessemer made large-scale structural steel cheap. The Industrial Revolution, in one real sense, was the moment when the chemical process that ancient bloomery operators had stumbled upon was finally scaled to the size that reshaped the physical world. That bloomery was still, at its core, the same reaction. Carbon monoxide reducing iron oxide in a hot enclosed furnace. The same accident, the same chemistry, billions of tons larger. One of the stranger disciplines in modern archaeology is experimental metallurgy. Researchers who build replica bloomery furnaces using ancient materials and techniques in order to understand exactly what ancient smelters were doing. These reconstructions are not guesswork. They are built using measurements of surviving ancient furnaces, analyses of slag deposits that reveal what temperatures were reached and what chemical compositions the ore and fuel had, and comparisons with ethnographic records of traditional ironworking communities that continued practicing bloomery smelting into the 20th century. When archaeometallurgists run these replica furnaces, filling them with charcoal and local iron ore, operating hand bellows for hours, and eventually breaking open the base to recover the bloom, they consistently produce metallic iron using only ancient materials and methods. The process works exactly as it must have worked thousands of years ago. This matters because it answers a question that once seemed difficult. Could ancient people, without any theoretical understanding, actually have developed this technology? The answer is unambiguously yes. The bloomery process does not require an understanding of chemistry. It requires observation, experimentation, and the accumulated practical knowledge that comes from generations of people doing something repeatedly and paying attention to what happens. Modern chemical analysis of ancient iron artifacts adds another layer. Portable X-ray fluorescence testing, scanning electron microscopy, and metallographic analysis of polished cross-sections of ancient tools allow scientists to determine the exact carbon content of ancient steel, identify which ores were used, reconstruct the temperature at which a blade was forged, and even determine whether a tool was quenched in water or air-cooled. Ancient artifacts carry their own manufacturing history encoded in their microstructure, readable with modern instruments. Several myths about the discovery of iron persist in popular accounts, and the archaeological record has been fairly clear in refuting them. The first is the Hittite monopoly theory. For much of the 20th century, historians suggested that the Hittite Empire of Anatolia had discovered and closely guarded iron smelting technology, releasing it only when the empire collapsed around 1200 years before the Common Era. This theory was based on a handful of cuneiform texts that seemed to describe iron as a closely held Hittite product. The archaeological evidence does not support this. Iron smelting sites and iron artifacts have been found at comparable dates across Anatolia, the Levant, Mesopotamia, and the Caucasus, with no evidence of a centralized monopoly. The Hittites used iron. They did not own the technology. The myth of the Hittite monopoly reflected how early 20th century historians expected technology to diffuse from a single source outward rather than how it actually tends to develop, which is in parallel across multiple sites as similar conditions produce similar solutions. The second myth is the single brilliant inventor. No person discovered iron. No culture holds the foundational patent. Iron emerged from thousands of small improvements, observed by individuals who did not know their observations would accumulate into a revolution, passed to apprentices who refined them slightly, spread by migration and trade to other groups who adapted them to local conditions. The history of iron is the history of uncredited incremental progress. The third myth is that iron immediately replaced bronze because it was immediately superior. It was not in unrefined form. Wrought iron was softer than good bronze. The superiority of iron only materialized after the carburization, quenching, and tempering techniques were developed, a process that took centuries. The transition to iron was not a revolution that happened in a generation. It was a shift that unfolded over hundreds of years, in different places at different rates, as the full toolkit of iron metallurgy matured. Stand in a modern city and look up. The frame of the building above you is steel. The beams that hold the floor beneath your feet are steel. The rebar embedded in the concrete of the foundation is steel. The bridge you crossed to get here, the train that brought you, the ship that carried the goods in the shops around you, all steel. The cars on the road, the cranes that built the buildings, the pipes carrying water, the cables carrying electricity. Steel and iron, in every direction, Every single gram of it was, once, iron ore, dull, reddish rock pulled from the ground. Every gram was put through a furnace where carbon monoxide stripped oxygen from iron oxide and left behind metallic iron. The chemistry running inside a blast furnace in Pittsburgh or Wuhan or Duisburg today is the same chemistry that ran inside a clay bloomery on an Anatolian hillside 3,000 years ago. The scale is different by a factor of millions. The underlying reaction is the same. What started as an accidental encounter between iron-bearing rocks and a charcoal fire in a copper smelter's furnace, observed by someone who had no idea what they were seeing, became the material foundation of the modern world. This is not metaphor. The connection is direct. Every generation of metallurgists, from ancient bloomery operators to Henry Bessemer, to the engineers who designed the arc furnaces used in modern steel recycling, was working with the same material, the same chemical principle, and the same fundamental problem of controlling how much carbon enters iron and what happens when it cools. The ancient person who first extracted a bloom from a hearth and found that hammering it made metal. They were not standing at the beginning of a separate story. They were standing at the beginning of this one. If this journey from meteorites to modern skyscrapers has captured your imagination, please like this video and subscribe to the channel if you haven't already. It takes just a moment and means everything for reaching more curious minds. Thank you for watching, and as for what comes next, there may already be a material waiting beneath our feet, as common and overlooked as iron ore once was, that will define the next great chapter of human civilization. What it is and how we might unlock it is a story still being written.